Hi folks, we're going to take a look at page 269, number 18. So here they give us a cylindrical can and they give us the volume of 500 milliliters that it has to hold, and it asks us to determine the dimensions that will minimize the amount of metal used. All right, and they just tell us to assume that the sides, top and bottom, are all the same type of metal, same thickness. Okay, so let me start with the diagram here. So I'm making my cylindrical can, okay, and we want to minimize the amount of material required. So if we're making the can, we're looking for just the exterior. So what I'm looking to minimize is the surface area. All right, now the surface area of a full cylinder is 2 times the base, the 2 circles, plus the side portion. So what I'm going to need as my dimensions are radius and height. So we have 2 times pi r squared plus 2 pi RH, which gives us the area of the lateral side. Okay, and as we often have in these problems is we have a function area in terms of 2 variables. So what we need to do is whittle that down to 1 variable, and luckily they do give us an extra piece of information. So 500 milliliters, the same as 500 centimeters cubed of liquid. So we're going to use that volume to help us write 1 variable in terms of the other. So we know that the volume is given by the area of the base, pi r squared, times the height. All right, so we know that that volume is 500 centimeters cubed times pi r squared h. And so what we can do is solve for one of these variables and then substitute that back into the function we're trying to work with. All right, now here, given that we have both an r squared and an r, it doesn't make sense to isolate either r or r squared, but what we should be doing is isolating the h. That'll avoid bringing any square roots into our equation. So that's 500 over pi r squared. So now let's do the substitution. So 2 pi r squared plus 2 pi r, and h will be replaced by 500 over pi r squared. Okay, got a little reducing here that goes on, and so our final function for the area is 2 pi r squared plus, so we're left with 1,000 over r. All right, and here we know for sure that r has to be greater than 0. So now I notice that I'm not working with a closed interval, so I'm going to have to be showing that what I get does indeed give me a minimum value. All right, so now that I've got my model with my domain, I can now go ahead and do the calculus portion. So we're going to take the derivative to look for our critical points. So here, derivative of r squared is 2r. So here we have 4 pi r plus, okay. So think of this as 1,000 times r to the negative 1. So we have negative 1, r to the negative 2 times, of course, 1,000. All right, so what we want to now find is when this derivative is equal to 0. So we've got 4 pi r minus 1,000 over r squared. Okay, and so we're left with this rational equation to solve, and usually the best way to solve a rational equation is to multiply both sides by the common denominator, which is going to be r squared. So multiply both sides by r squared. This remains 0. Here we have 4 pi r cubed minus 1,000, and now this is an easy polynomial equation to solve. So 4 pi r cubed equals 1,000. R is going to be equal to the cube root of 1,000 over 4 pi. All right, so it looks like we have just one critical point at this point here. Since it's a application question, I'll not leave it in exact form. So here we've got 1,000 divided by 4 times pi. Okay, and cube root, so exponent 1 over 3. All right, and it looks like we've got about 4.3. Okay, it's approximately equal to 4.3. So now let's test that this is indeed relating to a minimum value. All right, so we know that r starts at 0. Okay, so 4.3. So I'll take 5 on one side and I'll take 1 on the other side. And so our derivative, okay, I'll use this version here. So if we put in 1, there we go. So we can see this. So what do we have? We have 4 times pi times 1. Okay, then minus 1,000 over r squared, which is just 1. So here it looks like we've got a negative value, which, is what we're hoping for, since we're hoping this is going to be a minimum. And now let's put in 5. So 4 times pi times 5, okay, minus 1,000 divided by 5 squared, 25. Okay, and we see that we have a positive value. Okay, so since this goes from negative to positive at this critical point, we know that we have a minimum. All right, so now what we have to do is go back to the question and see what they're actually asking us for. Are they asking for the maximum area? Are they asking for the dimensions? So we go back and we see that what they're looking for is the dimension. So what I've already found is the radius. Okay, so here, therefore, the radius is 4.3 centimeters. Okay, so since 500 milliliters represents 500 centimeters cubed, these dimensions are going to be in centimeters. And now for the height, I'm just going to use that relationship I found earlier. So 500 divided by pi times 4.3 squared. So let's calculate that. So we have 500 divided by pi times 4.3 squared. Okay, and there we've got around 8.6. Okay, now you'll notice here that the height is exactly double the radius. Okay, and when there's no other conditions on a cylinder, the optimal cylinder will be the one whose diameter is the same as the height. But we couldn't assume that. We needed to show that using these steps. Okay, so just to recap. So step number 1, get yourself a good diagram if it's something physical in nature. Okay, determine that thing that you're trying to optimize, in this case your surface area. When you've got a function that's given in terms of 2 variables, your next step is to write that model in terms of 1 variable. In this case here, we use the fact that we were given this other piece of information, the volume, to write 1 variable in terms of the other. And then from there, you just do the calculus. So take the derivative, find the critical points, determine the behavior of those critical points. In this case here, it indeed gave us a minimum value, and then go back and check to see what the question is asking you for. In this case here, it was the dimensions. All right, that's it for this one.